For this question, it's a free fall. We've got a stone dropped from rest. That means V0 equals 0 down a water well. So, she drops the stone like this and it's going to free fall. She hears a splash after 1 seconds. We want to know the distance from the where it's dropped to the water. So how long does it take? Well, our strategies for these involve our average velocity, which is delta x over delta t. In this case, we don't know the average velocity. We do know the change in time, 1.6 seconds, but we also don't know the delta z. So we have two unknowns. We also have v equals v plus v0 over 2. We know the v0 is 0, but the average velocity is v over 2, so the final velocity is 2 times v bar. So again, we have two unknowns. So second, we can go on to our average velocity table. And we've got time 0, 1, 2, and our velocity, which will be 0, 10, 20. Average velocity, I stopped at 2 seconds because the whole thing ends at 1.6. So we got an average velocity is meaningless. And then we've got 5 and 10. And delta z is the average velocity times the time. So 5 and 20. So we know the answer is somewhere between 5 and 20 and impact velocity between 10 and 20. But it doesn't give us a precise answer we're looking for, but we've got a way to check our answer that we might work out in steps 3 and 4. So 3 is v equals a t plus v0. So v equals a t plus v0. And our acceleration is minus 10. We have 1.6 seconds. So we know the impact velocity is going to be 16 meters per second, which our table told us is it's in the ballpark. But we still don't know how far it is. So we go on to step 4, and we've got z equals 1/2 at squared plus v0t plus z0. And let's see, we're looking for z. We've got an acceleration of 10 and 1.6 seconds squared. Initial velocity is 0 and the starting position is 0. So we have z equals 5 times 2.56. And that gives us 12.8 meters. And so to two significant digits, that would be 13 meters. And the reason it's two significant digits is because we're given 1.6 seconds. So that's going to determine that. So the distance between that would be 12.8, which is 13 meters. For that question. Now the second question asks for the speed when it hits the water. Well, we actually already did that over here. So that just, we put that there like so, and so we're good to go. We've already solved that. So now we've got the stone hitting the water, and once it hits the water, it rapidly reaches terminal speed. So what that means is delta V over delta T is large. It's big as it falls through the water. So it leaves her hand at time equals 0. Time equals 0 is leaves hand, hits the water at T1, hits water, and T2, it lands on the bottom. And so we want to sketch how the speed varies from t equals 0 to t over 2. So this is a good time for us to pause and do our oizerga. So our origin 0, 0, that's good. Y-axis velocity, x-axis time. Our intercepts, we're not interpreting it, so that stays blank. We can read velocity time. The slope, delta v over delta t, is the acceleration. And the area, v times t, is the displacement, or delta z, meters per second times seconds. So we know we start at 0. So the y-intercept should actually be 0. At time 0, the velocity is 0. Hits the water at time 1. Well, during that time, the acceleration is constant. We know the speed is going to increase and the acceleration is constant. The acceleration is the slope, so there's some value up here it gets to, some maximum speed, and it's a straight line because the acceleration is constant. All right, so what we know is that it's going to fall through the water and be at terminal speed when it hits the ground. So it hits terminal velocity fairly quickly and then coasts at even speed to the ground. So there's going to be some speed it travels at as it reaches the ground. And it won't be accelerating. So we know that there is some kind of horizontal line. Acceleration is 0, slope is 0. Well, the question is, after it hits the water, is it velocity higher, greater, or lesser? Is it faster or is it slower than when it was in the air? And that becomes pretty obvious to see it's going to be lower. It's going to be less. So we know this part of the graph then has to be lower and it has to be horizontal. So our possibilities are this, that, and that. Now, we know in the beginning it said that it rapidly reaches terminal speed. So it gets there very quickly. And that is going to be the case here. The rate of change of velocity, the acceleration, is going to be very large. So that's very steep, and it gets less and less and becomes 0 as it stabilizes. Notice we use our tools and we focus in on where the endpoint is and what it does immediately afterward, and we can home in on it. And the last question, a free body diagram is a picture of the forces acting on a body. So here is the stone or the pebble. Now, when we spoke about terminal velocity initially, we spoke about us falling through the air as we're skydiving. And as we go faster and faster, we have more and more collisions. And those greater number of collisions have an increasing effect on us. And so eventually at some point, the number of collisions we're having provides exactly the same force as gravity, so that gravity doesn't have the effect of accelerating us. So at that particular point, at terminal speed, the forces are balanced. So we have force of gravity downward like this, and we have a force of drag upward. And those two will be equal and opposite to each other. Drag pushing upward and gravity pulling downward.